Pleasure to hear from Brown University about global axisymmetric order.
Thank you. Thank you very much. First of all, I'd like to thank the organizers, all of you, for a very kind invitation. It's certainly a great pleasure to visit such a beautiful institute. Yeah. And also personally, it's certainly a great honor for me to speak at this Maxwell Institute, because I realize large part of my work are related to Maxwell, either through his theory for electromagnetism or his kinetic theory for dilute gases. Since Zhu Zhang has spoke about the singularity, so I would like to speak something which is a bit tangential to the main theme of this conference. So I'm sorry about that. So what I would like to talk about is that I'm looking for a dispersive physical effect, so then we can suppress the singularity, right? Can prevent the singularity. And the model is a incompressible Euler equation. So let's consider the incompressible Euler equation. Here, the velocity field is given by U, and pressure is P. This is U grad U is the nonlinear convection. We assume incompressible flow, so that divergence of U is zero. So these are the usual Euler equation for incompressible fluids. We are considering a new effect. So this term E3 is the vector. There's 0, 0, 1. Okay. So this effect represents a constant rotation. Okay. So this is a classical Euler equation. However, in the presence of a constant rotation. So Euler equations describes so-called ideal fluids. So these are good equations, good approximations to the real fluids, so-called real fluids. In the case when you consider a fluid which is of large scale, and also in the absence of a boundary effect, and also for Reynolds number, which is very, very large. So in those circumstances, we know that you can ignore the viscosity forces, right? So it is this system we're going to consider. Okay, So it is important to know that if we ignore the pressure, then this classical incompressible Euler equation really behaves like a transport equation, in particular near U equal to 0. So then you do not in general expect any decay. Okay, This is one of the reasons why this problem is very hard, even when we armed with small data techniques. So the inclusion of this physically dispersive effect provides a linear decay. Okay, so that's the point of this project. Okay, so indeed, this rotation plays an important role in a lot of physical problems in geofluids. Okay, for instance, like ocean. Okay. So this could represent, for instance, a Coriolis force from the Earth's rotation. So I will talk about our motivation for this problem later on. So certainly this is this effect is physically important in some of the problems. So we're looking for solutions with axisymmetry. Okay. So the definition of that is let's assume that E theta, ER, EZ are the basis for vectors in cylindrical coordinate system. So now I can represent this velocity field in terms of those vectors, And then we have correspondingly U theta, UR, and UZ in front of those bases. So we say a solution is axially symmetric, right, with axisymmetry, if those components do not depend on theta variable. Right. Similarly, we require that the pressure only depends on T, R, and Z as well. Okay, so it's very easy to see that this form a closed system of PDE. So we're looking for a solution with this symmetry. I want to draw your attention to this component U theta. This component U theta. So this turns out to be a important quantity. So this is a so-called swirl in fluids. This is so-called swirl. So let me state a formal result of our project. Okay. So this is a joint work with my colleague Benoit Passadeur and Widmer, who is now in Zurich. Okay. So let's consider a initially smooth axisymmetric velocity field, and it is small. Okay, in some topology. Okay. So then there exists a unique global solution, okay, with a non-zero swirl. U theta is non-zero. Okay, so that you have the 1/T decay, which is the linear decay rate in the presence of this rotation. So this is our result. This is our result. So now I'd like to make some comment. I want to make some comments about this result. So first of all, it's well known that in two space dimension, let's say depend on X and Y, we do have a global large data classical solution to the Euler equation. Okay, we do have that. In the axisymmetric case, okay, so if there is no swirl, okay, so this is for the original Euler equation without rotation. Okay, so now if there's no swirl, okay, so swirl the U theta equal to 0 is a invariant. Okay, so in other words, if you start with U theta equal to 0, then if you're smooth, right, then this U theta stays 0 for all time. Okay, so this is the invariant for the original Euler equation. Okay, original Euler equation. So yeah, so also you have a global solution with large amplitude when you for axisymmetric flow, but with a zero swirl, with a zero swirl. There have been a recent breakthrough in the problem for 3D Euler equations, 3D Euler, the formation of singularity. So before, actually, people had a lot of experience and also evidence that turns out that this the swirl makes a big difference in the Euler theory. Okay, in the Euler theory. So people were convinced that one should be able to find formation of singularity, not necessarily in the general 3D setup for Euler, but rather than looking for a axisymmetric flow with a non-zero swirl. Right. So indeed, this is the case. So one of the so in recent breakthrough, one part is numerical, done by the group of my colleague Javi Gomez Serrano. Where they observe numerically, right? Numerically has a very strong evidence to show that you need formation of singularity for 3D, but with axisymmetric flow, okay, with non-zero swirl, okay, non-zero, but with a boundary condition, okay, with a boundary condition. Okay. And this later on was proven, okay, by using computer-assisted proofs, okay, the so-called interval arithmetic, say, by the group surrounded by Tom Howe, just very recently. Okay. So, so this is for the original Euler. Okay. So now, once you impose this rotation, so then, as I said, so then we will create a linear decay rate from such a rotation, and also in the presence of the this rotation, the u theta equal to 0 is not invariant anymore. Okay, so even you start with a u theta equal to 0, you can create u 0 is not 0. So generically, the u theta is never 0 when you have the rotation. So this work was based on an earlier work about the same problem for constructing almost global flows. Okay, so this was done in addition to 3 of us and also Trinh and Huang. Okay. So here I would like to say a little bit about the axisymmetry. Okay, so the assumption of axisymmetry serves as a way to rule out the 2D Euler flow. So indeed, turns out the 2D Euler flow also are exact solutions to the problem with rotation. It's very easy to check. Okay, but for 2D Euler flow, we know in general they do not decay. So in other words, this 2D Euler flow cannot be if there's a 2D Euler flow, then our result cannot be true, right? Because it's decaying. Right? So the axisymmetry certainly is one way to rule out such a 2D Euler flow. Okay, 2D Euler flow. As a matter of fact, 2D Euler flow serves as an optical to our result. It's not a counterexample because our solution demand finite energy. So in particular in the z direction, you have a 2D Euler flow which is dependent only on x and y, right? So that's you have infinite energy in terms of the x, y, z interval. So this is so a 2D Euler flow really serves as a obstacle to obtain our results. Okay. So later on, I'm going to talk more about what is the mathematical reason, right? So what we use the axisymmetry in a crucial way. So this is a brief introduction of our result. Okay. So the result, the proof of the result is quite complicated. So what I would like to do is go over a short history and also give a introduction of the general methodology we're going to use. And then at the last, I'm going to try to point out what are the main difficulty, what are the novelty of our work. Okay, so this is what I'm going to do. Okay, so first of all, I want to just go over some very brief history. So the problem in general is we try to construct small data result, right, in a dispersive system. Okay, in a dispersive system. So here we have a dispersive effect due to the presence of the rotation. So one origin of this result is so-called this is the study coming from the field theory, actually, an equation from the field theory, right? So one model problem I'm going to consider is a so-called Klein-Gordon equation, nonlinear Klein-Gordon equation. Okay, so this was a collection of work by Siegel, Strauss, and Morowitz, starting from 60s, 70s. Okay, so the model problem is this a nonlinear Klein-Gordon equation. Our goal is try to construct global small data solutions, right? Because they were interested in the scattering for this problem. Okay. So the mean machinery we know now is really classical. So the idea is you try to combine with a high order energy estimate with linear decay estimate. So combine these two together. So the linear decay estimate for the Klein-Gordon now is classical. Okay, can be written like this, right? So this is a so I can rewrite this in the Fourier space. Okay, so now by using stationary phase, now it's a little bit modern language, right? Stationary phase or finite propagation of speed. You combine these two, you can get this following estimate. Classically, of course, people were using the solution formula. So here, the important thing is we get a integrable decay estimate, right? There's the halves. Right? Now we have a number of derivatives, but that turns out not important. Here, I want to point out this is when you try to do Fourier analysis. Here, the natural norm appear here is the Fourier transforms L infinity. Okay, of course, by duality, right? It's very easy to control this by the L1 norm in the physical space. Right? So this actually is usually the L infinity L1 norm is usually what these people use. But turns out there is a lot to say about this norm. Turns out this norm is more fundamental. We will see that controlling this Fourier transforms L infinity norm turns out to be more fundamental in somewhat a more modern approach. So this is the linear decay estimate for linear Klein-Gordon. So in the 60s and 70s, what they could do, those pioneers could do, is they could solve the problem with cubic nonlinearity by using the interplay of L infinity and high order energy estimate. Okay. However, they couldn't do the case with quadratic nonlinearity. Okay. So let me briefly convince you what was the problem. Okay, so if we try to do high order energy estimate, schematically I'm multiplying this multiplier, right? Where this partial denotes arbitrary spatial derivatives of the, let's say, case order. So now when you try to do the important thing you want to do is you try to control this 0 to t integration. This is your biggest enemy, right? So what you can do is you can try to use the Leibniz rule. You can pull out, by the Leibniz rule, you can pull out a L infinity norm of half size of the derivatives. You're willing to pay a lot of derivative, right? So now this part is more or less energy. So now if you can show this integral in time integration is bounded in terms of the energy, which is L2 type, then you're okay. Then you can close. Then you can close the whole process, right? Then you can close the whole process. So indeed, this is a case when you have cubic nonlinearity. Why? Because now, in order to close this, I have to introduce another layer of estimate, which is the L infinity, right? So now I treat this F, the nonlinear term, as the forcing term. I'm using Duhamel, right? When I use that, you can see then I get something like this. So here I'm using the linear decay estimate L infinity to L1. Right? So here gets 3 half. So now the question is whether or not you can estimate this in a closed form. Right? So when you have a U3 cubic power, because it's here we have L1, then we know that I can pull out the L infinity, and then I still left with U square and then L1, which is nothing but exactly L2. So then I'm okay. So I can close L2. Right? This is in terms of energy. So then cubic I'm okay. However, for the quadratic, it's a different story because in this case, when I pull out a L infinity, I'm still stuck with a L1 norm. So the result I'm talking about is always in the whole space. So where you can exert the most of the the dispersive estimate, okay, decay estimate. So we know in the whole space, L1 is not equal, is in some sense stronger than L2. So this is, you cannot go back to the energy. That's why you have a problem. Yes. So this fundamental difficulty was solved in the 80s by two very different methods. One is by Klein-Gordon, right? So this is a so-called vector field method. So what he did was he observed that because of the problem of Klein-Gordon and related problem coming from the field theory, which is inherently Lorentzian invariance. Right? That's how you build the field theory. So in particular, so the generators of the Lorentzian group, right? So those are commutative or almost commutative with the linear flow. So that means instead of looking for standard energy estimate, I can employ those vector fields as my basis for taking. So once I employ those more vector fields, actually I can get this type of estimate, L infinity L2, if I can use this vector field. So now this is become classical. So as we can see, then this is led a lot of development with a hugely successful method, right? So people now refer to vector field method. Okay. So independently, there is a Shatat method, which is so-called the normal form method, right? So interestingly, both papers published in the same issue of CPN, both beautifully written papers. So Shatat method actually uses a completely different idea, right? So the idea is, well, we know how to solve the cubic problem. So let's see whether or not we can try to reduce the problem to a cubic problem. Okay. So now he seek. So inspired by the Poincaré's normal form for dynamical systems, right? He seek a transformation for the unknowns. So in other words, this is our original unknowns. He looked for a new unknown V, where we have a transformation B there. Okay. So so the goal is to seek such a quadratic transformation B, so that when I plug this equation for V, the quadratic terms in V vanishes. So if I can do that, then clearly in terms of V, I have a cubic equation I know how to solve. So once I can solve V, then I can solve. So the question, so he showed that for Klein-Gordon, you always can find such a V. Okay, understand? Two very different method. Actually, in terms of norm, everything are completely different, but they're solving the same problem. Okay, solving the same problem. Two very beautiful methods. Okay. So for Shatat's method, I actually so I used that in my earlier stage of my career. So certainly it's a very nice method. However, it's a little bit mysterious how he could construct this B, which is not clear. Okay. So now there's a more modern viewpoint, so that we can see the B very clearly. Okay. So now let me give you an overview of this new formulation. Okay, new formulation. Okay. So this new formulation was due to Shatat himself and also Masmoudi and Germain. Okay, Germain. So the key quantity to introduce is this profile. This profile. Okay. So what is a profile? So U is a solution to the nonlinear equation, right? So now let's assume this is the conjugate. So let's assume the linearized flow is in Fourier space, e to the I lambda CT. And this is the so-called conjugate flow, on the negative side, right? So I define for any nonlinear solution, nonlinear flow you had, I define this guy. I call it F hat. This is the profile. Oh, what is the meaning? What is the meaning of this profile? Well, we see that when let's assume the solution, the problem is a linear, exactly it's a linear problem. So in that case, if it is a linear problem, then we know U hat exactly e to the is e to the I could see lambda could see t u naught, right? U hat naught. Okay. So in the linear case, this exactly gives you go back to U hat initially t equal to 0. Okay. So in the linear flow, right? In the linear problem, then exactly you go back to initial condition, right? Initial condition. Well, the most important thing when you try to study this almost a linear problem or small deviation, so is that you would hope your nonlinear solution behaves very much like the linear flow, right? That's your hope to construct solution. So indeed, if my U hat is almost like a linear, almost like a linear flow, then I would be not exactly the initial data, but it's almost data. Right? So the profile basically means you're almost back to the initial data if your flow is almost linear, right? Behaves almost like linear. So the most important thing here is now the profile. There's no way the profile decays now. So it's really like a linear flow. So this is really, in some sense, you can think about this almost independent of the initial condition, independent of the time variable. So this is. So this should be stationary. Okay, so now the important thing is to try to study the problem, okay, for this profile. Now you try to rewrite the problem in terms of the profile, see what you can do. Okay. So this is one important characteristic of this profile. Basically, it's almost stationary. So now what you can do is you can rewrite the nonlinear equation in the Fourier form, in the Fourier space. Now you just concentrate on the quadratic nonlinearity. You're not cubic. It's not important. So the when you do Fourier transform for quadratic nonlinearity, then this is determined as a convolution. Right? This is the m is a multiplier. So this is the original equation. Now you know by the definition of the profile, this guy exactly is f hat t derivative. So now what you do is you just integrate on the right hand side, and then now you replace u hat by f hat everywhere. Okay, everywhere. Notice they have different frequencies, right? So then that means by definition I have to pay this different frequency. So in the end, you get a equivalent form of the equation for the profile of this following form. You have a very complex the phase interaction part, which is this part. So now you have this equation like this. So the goal is still, this is a nonlinear problem. You still want to control the time integration, right? So now you denote this is important quantity, so-called interacting phase, right? The important thing is that we denote this interacting phase. Now we can see when we try to control the 0 to integration, this doesn't depend on m, doesn't depend on s, doesn't depend on the time, right? And neither these two, because we assume they are almost stationary at the time equal to 0, right? So those are the profiles, right? So in other words, there's no way we can hope to get any decay from these three terms. The only decay we can get is from this guy. So the nice thing about this new formulation is to identify the key difficulty, right? Key difficulty in your process. So now we can do several things. For instance, if this phi is not 0, suppose this integrating phase never 0, that's exactly the case when you have a Klein-Gordon, you can show. Okay. So then what you can do is now you can try to use this simple formula. So we try to recover this guy, right? This is this. So now I use this simple formula. So this is the I phi of the thing I want to represent, right? This is the same thing. So now since if phi is not 0, I can divide this through. Right? I can divide this through. So now I can divide it through, and now I can do integration by parts in S. If I do that, there's one term will be hitting on the other integrand, right? The other integrand, which I will write in this form. And then there is also two boundary terms at t equal to 0 and at t. We don't worry about the t equal to 0 term, and then this is the term at t. Turns out this is nothing but exactly was the normal form Chatat constructed. So this exactly is his normal. That's the explanation of his somehow mysterious method. Okay. So as long as your interacting phase is non-zero, okay, then you can make his process. Make this process, this is his normal form. And now if you look at here, this is ds theta on this f. Now I use this equation again. This guy is quadratic. This guy is quadratic, and now I have another guy, so it's cubic. So we know cubic we can solve. So that's the reason why. That's the reason why this problem is solvable. This is the reason why this problem is solvable. So this is one way. Another way is suppose I know the interacting phase, the eta gradient is not 0. Let's assume. So now again, I want to represent this guy, right? I want to represent this guy, which is appear in this integral. So now again, I use this formula. Once I use this formula, you see when I take eta derivative, there's a SIS coming down. And then I have this derivative, right? I have this derivative. Assume this guy is not 0. Again, I can divide. Right? Again, I can divide. Once I can divide, now we can see that when I make this division, then there is a 1 over s coming down. Of course, there are some other norms I have to struggle with. But the important thing is I can extract a 1 over s, which is almost integral. Okay, which is almost integral. So of course, provided I can control this guy or this guy. Almost. So okay, so we have two mechanisms, right? So as long as either this is not 0 or this is not 0, we can do either way, right? We can have a mechanism of beating this 0 to t integral. The worst case is suppose I have a set where both are 0, right? Both are 0, of course I cannot do neither of them, right? So so if this guy is empty, right? So if we call this set space-time resonance set, right? If the space-time resonance set is empty, then we're in good shape. In some ways, we can always have a mechanism try to beat the 0 to t integration. Right? Otherwise, it's difficult. But even if this space-time resonance is non-empty, but if along this set, right, which is a set in the phase space, if my multiplier, the nonlinearity, happen to be exactly 0 when this is the resonance set, I'm still okay because this is as if nothing happens, right? As if I can always do this two process. So this nonlinearity satisfies this form is exactly the null form. This was introduced by Klein-Gordon in 1984, I believe. So this is one. This is one advantage of reducing this profile function. Another advantage is just by definition, right? So once I can control the profile in the L infinity norm, forget about the derivative, right? Suppose I can control it, then by the virtue of the definition, automatically I will obtain a sharp linear decay rate for the unknown in the physical space. That's just by the nature of the definition. So there are two things important, two important characteristics of this profile. Why this is good. So once again, here you can see the profile of the infinity norm is very important. Why very important. So now I want to go over two very simple but fundamental estimate, okay, in terms of this new quantity, okay, the profile, okay. One is, let's try to control this nonlinearity is L2, okay. So if you do that, you can go back to the previous definition. You try to regroup them and make an inverse Fourier transform. Okay, make an inverse Fourier transform, and then you can rewrite this estimate, okay, by the decay estimate. So in other words, if you want to do L2 estimate, you can easily see this is bounded by a sharp decay, linear decay in terms of the L infinity norm of the profile, as well as L2 norm. So this is one basic estimate. The other basic estimate is when you try to estimate the L infinity norm, this nonlinearity. That's even simpler because in this case I just use Cauchy-Schwarz, okay, bounded by F hat L2. So these are two basic but very useful estimates. So now let me try to rerun the previous estimate now in this new quantity. Okay. So now we can use this. Let's assume that we'll have phi is now 0. So now in this new language, right? So this profile is on infinity norm, which is the key quantity to keep track. As a matter of fact, all the examples unknown today, I think they always, in all the schemes, you have to guarantee this guy is always valid. All right, so this is so if you want to estimate this term, you use this normal form transformation, and then this is a quadratic, right? Quadratic, now you have L2 times L2, right? You want to estimate L infinity, and then the L2 again. This is a quadratic again, right? So now the L2 quadratic is bounded by sharp decay on the L infinity, and then another copy is coming here. So you see here L infinity is L infinity, right? So once this P is bigger than 1, clearly you can close. Right? Clearly you can close. So when this is not 0, right? Let's assume this is not 0. We can do one integral by parts, something like this. But this is not enough. Just exactly have a logarithm. So usually you have to go more, right? One more. So then you have to estimate, for instance, right? You have to try to estimate something like this, so on and so forth, so on and so forth. So this introduces a new type of estimate. So indeed, by using this new method, we can construct Germain, Masmoudi, Chatat, they can construct the global waterway. And then in a very important work of Ionesco and Posada in 2012, they were studying a model problem, Klein-Gordon problem with two speeds. So in that case, the space-time resonance set is actually not empty, but actually is usually is a 2D sphere. So the measure is somehow in 3D is small. Okay. So in order to overcome this difficulty, they introduce a very comprehensive approach. Okay. So the main idea is you try to do either integral by parts or normal form transformation away from the sphere, and then you try to play with the small measure of the sphere in order to interpolate, right? In order to get the result. Okay. So in order to do that, you have to track, because the decay rate depends on the phase space where you are, phase space, and also depends also on the nonlinearity. Okay, and also depends where the time is. Okay? So in order to take into account of all of these effects, what they did was that they introduced a standard little Paley decomposition into in the phase space, into taking into account the little Paley in the frequency space, and also they decompose in the physical space, and then also chop out in time. Okay, in time, in order to squeeze out the interplay in order to close the estimate. Okay, So they call those atoms. In other words, this is a basically breakdown to the basic level. Okay. So then in basic levels, they can see what kind of norm you can propagate. Okay. And then you try to sum them up together. Okay. So when you break down everything, okay, you need to gain sufficiently. You have to gain sufficient. So then you usually when you break everything, you lose logarithmic accounts. Okay. You need to go to gain back. Okay. So this you need to design the norm, which is usually depend on each atom. Using the idea, the same machinery, we were able to construct solution to the Euler, so-called Maxwell system. So here, this is the Maxwell relation. So this is actually a important model for describing so-called full fluid model for plasma physics. So the important thing here, underline this is somehow there is I call it a Klein-Gordon effect. So when you have fluids interacting with the electromagnetic field, somehow this interaction create a low order term, like behave like a Klein-Gordon term, the mass term, Klein-Gordon term. That enhance the decay, So then, this is the reason you have an extra decay, so that you can somehow overcome this 2D, and also somehow also sum them up. Okay. So we were able to show this, solve this problem for so-called irrotational flows. Okay. So irrotational flow behaves like a wave equation. So you have natural decay. Of course, we know that for fluids, there's a irrotational flow, and also there is a rotational part, right? So formally speaking, you can split a fluid flow into rotational part and irrotational. Irrotational part is like wavy, natural decay. Rotational part like incompressible oil. There's no decay; it's just transport. Okay. So we are interested in whether or not we can generalize this problem with a rotational flow. Okay. So there, the most important thing we realize is for all this plasma problem, magnetic field, constant magnetic field, applied magnetic is very important. So indeed, this is the region we want to include the constant magnetic field there. But constant magnetic field, the effect is exactly like a rotation. Right. So this actually is our motivation of studying this project. In fact, the irrotational Euler, incompressible Euler is really a simplified model. Okay. Wow, purpose. Turns out this is very good starting. So certainly, I'm happy to say this. You can see another Maxwell connection. So I would like to say a few words about advocate for this method. Okay, this method developed by Ernesto and Posada. I think this is really a very comprehensive methodology when you try to study a nonlinear problem around a constant steady state. Very important. I see a lot of problems, for instance, in general relativity, right? You're studying something which is not constant, right? So this is, of course, this method cannot apply. Okay, when you have a constant background, let's say here is 0, right? So this depends on basically the methodologies that you break down into the atoms, right? You break down everything, and then you try to track the estimate for atoms, see which kind of norm you can propagate. At the basis of this atom, there's only 2 types of estimate, which I just introduced, right? These 2 basic estimates you can do. So this method does not depend on a single magical estimate, but rather a collection of different estimates you try to combine together. So in some sense, this is has a combinatoric type of flavor, right? So in the end, is how you can design a norm, how you can combine together. Actually, I enjoy a lot working in this this type of problem, even though I'm not trained as a harmonic analyst. But still, because in the end, it's the logical splitting of those cases, right? And then whether I can combine them efficiently. So actually you can certainly still make a contribution in this. So this is an overview of this general methodology. Okay. So now what's new in our product? Okay. So first of all, let me say the role of axisymmetry. The role of axisymmetry, mathematical role. Once we assume axisymmetry, then the space resonance set is empty. Okay. So if the axisymmetry is imposed, you have a huge set of space time resonance set, which is extremely hard to overcome. Okay. So this is one reason why axisymmetry is important. And the novelty of this problem is again is axisymmetry because if you look at the symbol of this operator, this is a linear operator, very simple. However, you can see this is a ratio, right? This is a ratio of the third component versus the length. Okay, so this ratio plays a very important role. So now if we try to consider this phase triangle, right? Before we have this phase triangle when they're homogeneous, right? So they are basically, even though they could be complicated, but you know, they only depends on the length. However, here now we're much more singular. Indeed, when this ratio goes to either 0 or infinity, right? So the second operation, when you take a integration by part in eta, will create significant singularity. So you have to control. So this is the key difficulty. So we have to introduce a new machinery, new framework to take into account of this loss of this ratio, basically this ratio. Okay, we have to design norm according to this ratio, and then in the end is this this ratio versus the nonlinearity, okay, and also these two basic estimate, right? So sometimes you need to gain some volume in order to compensate, okay, and compensate this in a very delicate way. Okay, so I would say the novelty of our paper is a new framework to deal with the non-isotropic symbol, right? Non-isotropic symbol in a systematic way. Nonlinear, of course, nonlinear, right? The difficulty is nonlinear because you can imagine for each one of them have to split, and then I mean there's a combination. Each one of them have to split, right? So the cases are enormous. Okay. So let me just reveal the norm. Okay, so luckily we can use a angular Littlewood-Paley decomposition in this case to make our counting, right? Each the splitting more efficient. Okay. There's our norm are quite complicated, but the most important thing I want to see, they are, even though they are L2 type of norms, but for instance, the first norm, you can see in terms of scaling that they exactly represent this important quantity I've had on infinity. And because I have divided the volume right in the correct order. So this is the soup. And then there's this norm taking into account basically this y is like a derivative, right? As I said before, you know, one derivative is not enough, just not enough. So somehow here we need a little bit more to make sure you have the integrability. So I'll stop here. Thank you very much for your attention.